The subject of this forensic evaluation is a Japanese military aircraft designated as the Kawasaki Ki-61 Hien, carrying the manufacturer construction number 379. Built in 1943, this airframe is most often attributed in public recovery records to either the 68th Sentai or the 78th Sentai, though the original unit documentation is incomplete. It stands as a unique structural outlier within the broader scope of Imperial Japanese aviation. The investigative objective is to evaluate the physical evidence that explains how this specific machine survived its operating environment, only to suffer severe structural compromise during its eventual salvage. This is a study of a forensic gap, examining the procedural distance between an intact machine in a remote location and a fragmented fuselage requiring complex restoration. Most contemporary fighter designs fielded by the Japanese military prioritized lightweight construction and utilized air-cooled radial engines. That engineering choice mandated a blunt, wide forward cowling to ensure adequate airflow over the cylinder banks. Airframe 379 broke completely from that established geometry. It was designed around a liquid-cooled inverted V12 engine. Integrating a 12-cylinder inline power plant forced a massive structural reconfiguration of the forward fuselage. The engine block itself was long and narrow, shifting the center of gravity and altering the load paths through the main firewall. That choice forced a new thermal system, coolant lines, or pumps and a ventral radiator, adding weight and vulnerable plumbing. In return, the cowling could be wrapped tight around the narrow block, tapering the nose into a sharp, streamlined profile. This aerodynamic profile reduced forward drag. It shifted the way the airframe traded speed, climb, and turning performance depending on altitude, power setting, and loadout, rather than describing a single, universal advantage. The sharp, pointed nose created a visual signature that contradicted standard intelligence expectations. When reconnaissance analysts first observed the narrow fuselage, some assumed it reflected a licensed European influence, and early reports sometimes misread the type before clearer identification caught up. That confusion complicated early tactical assessments and delayed confident recognition in the field. For decades, as the airframe rested out of sight, and open records still disagree on its unit assignment. Yet, establishing that identity is only the first step in the forensic process. The physical artifact that exists today is completely detached from the environment where it originally went down. It is separated from its flight controls, its armament, and a significant portion of its aft geometry. The surviving aluminum skin, internal bracing, and engine mounts are the primary witnesses now, and they have to be read for the structural limits they expose. The engineering tolerances that allowed the airframe to carry a heavy V12 engine also determined how the metal would respond to sudden deceleration and long-term exposure. Every rivet line and separated spar connection provides a data point, helping investigators rebuild the timeline of its structural degradation. The current state of airframe 379 reflects a severe documentation gap. Without continuous records, investigators can rely only on intrinsic evidence preserved in the remaining metal, including its 1943-era alloys. The challenge is to read these remaining structural clues to understand exactly what parameters govern the survival of the fuselage. The immediate question is what exact physical mechanisms allowed this specific airframe to survive its grounding intact. The physical geometry of a forced landing determines the absolute structural survival of any airframe. When the aircraft initiated a descent into a soft swamp near Cape Wom, investigators can only infer the final moments from limited mechanical scars. A cracked reduction gear casting and propeller blades bent rearward can be consistent with a forward strike at low power and a relatively controlled contact, but those marks alone do not prove full aerodynamic authority or a perfectly flat attitude at touchdown. Confronting a completely unpaved and saturated environment, lowering the standard landing gear was an impossible operational choice. Deploying the wheels into deep mud would instantly create a massive mechanical fulcrum directly beneath the center of gravity. This geometric trap would force the heavy forward engine mass violently into the earth, immediately flipping the airframe and snapping the main fuselage spine. The necessary decision to execute a gear-up belly landing prioritized maximum uniform surface contact over conventional landing protocols. By keeping the undercarriage securely retracted within the wing roots, the smooth lower fuselage skin could act like a sliding keel against wet swamp grass and mud. That broad contact helped distribute loads through the lower skin and keel structure rather than concentrating them at a single wheel contact point. The continuous friction generated by the saturated ground bled off forward velocity gradually. This controlled deceleration may have reduced the peak loads that drive a nose dig-in and catastrophic spar failure, helping explain why major structural collapse was avoided at the moment of contact. Once all forward momentum was finally arrested, the sheer dead weight of the forward engine block dictated the final resting angle of the wreckage. The aircraft settled slowly into the soft terrain, pivoting precisely on its center of gravity into a shallow but distinct nose-down attitude. This static settling geometry forced the lower engine cowling and the forward lower fuselage directly down into the stagnant water of the swamp. At this exact moment, the immediate threat to the airframe shifted from mechanical destruction to severe environmental degradation. Standard tropical environments can attack aviation aluminum through constant moisture cycling, salts, crevice conditions, and galvanic effects. Prolonged burial in waterlogged mud can, in some cases, slow visible surface oxidation by limiting oxygen exchange, but it does not guarantee preservation, and corrosion can still proceed depending on pH, chlorides, microbial activity, and trapped electrolytes. What matters here is not a simple no oxygen, no corrosion rule. It is but the specific chemistry that may have reduced the rate of the most obvious metal loss on the submerged panels. The exact elevation of this oxygen-depleted zone is not a simple forensic estimate. The standing swamp water permanently etched a distinct horizontal waterline stain directly into the factory camouflage paint across the entire forward cowling. This rigid chemical signature acts as the primary anchor proof for the entire crash site investigation. It maps the precise physical boundary between the perfectly preserved metal below the water surface and the heavily weathered aluminum exposed to the humid jungle air above. The stain anchors prolonged partial submersion, but it cannot on its own reconstruct seasonal changes or prove a sealed environment without site measurements. Even so, the submerged panels likely sat in a chemistry that slowed the most obvious metal loss, letting thin skins persist for decades where exposed aluminum would normally fail quickly. For 30 years, the airframe remained trapped in this specific environmental lockdown. The deep mud firmly stabilized the wreckage, completely preventing the heavy engine mounts from shifting or causing secondary structural collapse over time. The anoxic boundary protected the lower metal, and the remote location delayed immediate industrial salvage. But the same mud that held the wreck in place would become the unknown variable the moment anyone tried to pull it free. The extraction of the wreckage occurred in the early 1970s. Laws covering war surplus material and protected cultural property existed, but practical enforcement in isolated areas could be fragmented, and procedures resembling modern archaeological standards were not consistently applied. The recovery was conducted by a private individual named Roy Worcester, with the objective focused on retrieval rather than full forensic site preservation. In that era, permissions and oversight were often informal, and site recording routinely failed before extraction even began. The procedural trade-off was immediate physical rescue versus total data loss. Once the wreck was lifted and floated out, reportedly carried on a log raft and towed toward Wewak, the site context was effectively overwritten. Orientation, localized debris scatter, and other forensic anchors can be lost the instant extraction begins, long before any museum-grade documentation is created. When the heavy fuselage was finally pulled clear of the swamp, the distinct anoxic waterline preservation became immediately visible along the metal skin. This clear division of weathering proved that the structural integrity of the lower frame was entirely viable for sustained recovery. Worcester transported the massive, largely complete assembly out of the jungle environment and into a populated zone. The aircraft was then relocated directly to a private residential property in Wewak. The local decision was made to place the recovered airframe on open static display on a residential lawn in Wewak. This deliberate action transitioned the artifact from a buried crash relic into privately held, informal public display exposed to sun, humidity, and casual handling. In that phase, and the most coherent recovered elements, especially the fuselage section, remained together in a recognizable configuration, even if major components were already missing or incomplete. This period marks the last clearly documented chapter in which the recovered structure could still be read as a single, contiguous forensic object. The complete lack of institutional conservation meant no chemical stabilizers, corrosion inhibitors, or protective coatings were applied to the exposed aluminum metal. The surviving factory paint and the critical waterline stain remained visible strictly through natural material endurance rather than active funded preservation efforts. Even so, leaving it untreated did buy one thing: it kept the airframe out of scrapping and out of the jungle long enough for the next move. The true vulnerability of this specific recovery phase was not environmental, but purely logistical. Because the aircraft was deliberately kept fully intact, its massive physical footprint remained totally unchanged. A fully assembled military fighter aircraft is a highly restrictive, rigid object to manage within a standard civilian infrastructure. Moving it requires specialized transport equipment, wide clearance corridors, and significant financial resources. While the heavy airframe was secure on static display, it was essentially trapped by its own structural dimensions. It could not easily be relocated or protected from rapidly changing legal landscapes without severe physical intervention. The airframe was safe on open display, but a critical question emerged regarding what specific logistical limit forced its eventual disassembly. A rigid 39-foot wingspan could not be moved through ordinary routes or onto standard shipping platforms intact, so export preparation became disassembly by necessity. Tail removed, structure stripped, and the airframe reduced to shipping blocks. The trade-off was immediate: preserve a complete artifact or move it at all. Operators severed major joints without manuals or structural support, cutting through heavy formers, unbolting spars where they could, and separating control runs to free the wing panels. When bolts seized or lifting gear was unavailable, the work shifted to crude cutting through load-bearing members, permanently breaking engineered load paths and factory alignment. The physical process rapidly escalated from basic transport preparation into aggressive material stripping. As the airframe changed hands and priorities shifted from preservation to portability, valuable or easily removed components were taken out of the structure. By the time the fuselage entered later stages of private ownership and export planning, much of the armament-related hardware and cockpit equipment was no longer in place, leaving empty mounts, cut runs, and open bays that restoration teams would later have to interpret from fragmentary evidence. This uncontrolled disassembly produced component orphanization. The tail was separated without tags, diagrams, or oversight, severing the chain of custody in practical terms and stripping the artifact of its baseline as a single, continuous structure. The individual components lose their spatial relationship, meaning specific, localized damage or weathering patterns can no longer be interpreted across the whole airframe. This isolation strips the remaining parts of their cohesive historical value, completely erasing the flight control continuity and any impact stress signatures that existed on the aft frame. What survived was abruptly reduced, leaving later restoration work to start from a forward shell stripped of the reference geometry the aircraft once depended on. The remaining forward fuselage was fundamentally altered by the removal of the heavy tail and the dual 12.7 mm machine guns. Stripping the aft structure and the forward armament drastically shifted the center of gravity of the remaining hulk. This sudden weight reduction made the crippled forward section extremely difficult to balance safely on standard shipping cradles. The extraction was technically successful in moving the bulk aluminum out of the region, but it actively destroyed the historical integrity of the artifact in the exact same process. The original geometry of the machine was permanently gone. With the tail section completely separated and lost, the critical question became how the remaining stripped fuselage could be utilized. When Justin Hoisington exported the fuselage to California in the late 1970s or early 1980s, it arrived missing crucial aerodynamic control surfaces and primary structural reference points. The surviving forward shell held the intact V-12 engine block and the forward cockpit boundary, but without a complete aft geometry, verifying the original flight control layout became a forensic challenge. The export process successfully relocated the bulk material across the Pacific Ocean, but the resulting artifact was severely compromised. The arrival of this specific structural shell in North America shifted the operational challenge from physical extraction to complex technical cataloging. Receiving a stripped fuselage requires restoration teams to build a structural inventory based entirely on partial evidence. Every severed load path and empty component bracket must be analyzed to infer what was originally attached. Because the airframe was completely orphaned from its original tail section and primary armament, engineers lost the physical continuity required to draft a precise restoration template. The physical footprint of the artifact was significantly smaller, but the analytical workload increased exponentially. Justin Hoisington facilitated the transfer of the remaining bulk structure, successfully navigating international shipping logistics to bring the artifact into the American warbird market. The 1980s represented a specific era in aviation collection where stripped airframes frequently traded hands based purely on the rarity of the forward engine cowling. The value of this specific machine was completely tied to its unique liquid-cooled engine profile, making the forward section highly desirable even with the massive structural deficit at the rear. However, the missing aft structure created severe mechanical complications for basic ground handling. The aft fuselage contains the critical elevator bell cranks, rudder hinges, and tail wheel retraction mechanisms. Without these specific mechanical linkages, it is physically impossible to reconstruct the control cable tension requirements or the exact aft weight distribution. That missing data forces improvised ballast and bracing just to keep the structure stable during handling and storage. By 1985, visual documentation confirmed the exact state of the imported shell resting in a Chino, California hangar. The photographic evidence captured during this period verified the absolute limit of the surviving metal. The forward cowling still retained the rigid chemical signature of the swamp waterline, proving the forward geometry remained stable during the trans-Pacific shipment. However, the severed aft bulkheads presented a hard physical boundary for the restoration team. The missing vertical stabilizer and horizontal tailplanes meant that any future attempt to rebuild the aircraft would require drafting new engineering drawings from scratch or locating exact replacement parts from another surviving airframe. Inspecting the severed joints revealed the exact limits of the remaining factory metal. The condition of the severed joints at the rear bulkhead complicated any future attempts to splice new metal into the frame. Restoration engineers had to map every distorted rivet hole and torn aluminum panel to establish a clean starting point for structural mating. This meticulous cataloging process was absolutely essential to ensure that any future replacement parts would align with the original load paths, without introducing new stress fractures into the aged aluminum skin. The decision to hold the fuselage in long-term storage rather than immediately forcing a flawed restoration was a direct consequence of this missing geometry. Proceeding with a rebuild without the correct factory dimensions risked permanently altering the structural identity of the machine. Fabricating a generic tail section based on estimated dimensions would introduce severe aerodynamic instability and ruin the historical validity of the artifact. The trade-off was simple: fabricate unverified structures to finish a silhouette quickly, or stop and wait for authentic reference parts. The 1985 documentation captures the result: secure metal, hard cutoffs, and a rebuild problem defined by missing geometry. With the original geometry gone, any rebuild would hinge on replicas or donor structure, an unresolved problem that followed the fuselage into museum hands. Kermit Weeks acquired the incomplete fuselage of airframe 379 for his Florida Museum collection, completely inheriting the severe geometric deficit created decades earlier. The transition from private trading to formal museum consolidation shifted the operational priority to long-term stabilization and accurate physical reconstruction. The process of museum consolidation requires transferring the surviving bulk material into a highly controlled environment to arrest any latent corrosion deep within the remaining factory metal. Museum engineers must carefully inventory every surviving rivet line and bracket to determine exactly what structures are required to make the fuselage self-supporting. Without a cohesive tail unit to anchor the center of gravity, the massive forward weight of the V-12 engine continuously threatens to distort the lower belly skins. Securing the airframe for long-term display strictly mandates rebuilding the complete aft structure. Faced with the missing geometry and the practical need to present a recognizable silhouette, the museum pursued a documented compromise using components from another recovered Ki-61 often cited as airframe 640. In some configurations, tail surfaces or tailplane elements from that donor airframe have been associated with the display or mock-up of construction number 379, explicitly signaling where original material ends and substitution begins. Merging major structures from separate wrecks is not a simple plug-and-align operation. It requires careful fitting, reinforcement, and clear labeling so the seam remains legible to future researchers, and so no one mistakes a composite for an untouched survivor. That transparency matters because a hybrid airframe does not represent a single operational timeline. It represents a chain of recoveries, losses, substitutions, and curatorial choices. Today, the surviving components associated with construction number 379 are reported in long-term museum storage in Polk City, Florida, with major assemblies not necessarily kept as one fully assembled, self-supporting fighter at all times. The forward section still carries faint swamp-era signatures. The substituted aft elements remain a visible record of unregulated salvage and missing documentation. The remaining inquiry is how preservation teams will monitor and mitigate corrosion risks across original and substituted joints as the composite structure ages in controlled storage.